Hello everyone, we are Group 2 and welcome to our presentation of the final project for advances in 3D vision. The paper we have chosen to work on is titled Repurposing Diffusion-based Image Generators for Monocular Depth Estimation. It comes from the famous Institute of Photogrammetry and Remote Sensing at ETH Zurich, the Swiss Federal Institute of Technology in Zurich. To understand the context, what is monocular depth estimation? Monocular depth estimation determines object distances from a single image, a critical task for applications like robotics and augmented reality. However, traditional models struggle with new or unfamiliar images because they are trained on specific datasets and often fail to generalize. As objective, this work introduces Marigold, a new molecular depth estimation model using a diffusion-based generative approach. Leveraging extensive visual knowledge from these models, Marigold enhances depth accuracy, particularly in zero-shot scenarios where it predicts on unseen datasets. Our focus was to understand, reproduce, and enhance Marigold's performance on novel datasets. As mentioned earlier, molecular depth estimation is essential for various applications. At the technical level, molecular depth estimation is a dense structured regression task, and this task has been enhanced a lot with advances in deep learning, with convolutional neural networks and transformers. Marigold is the proposed model for molecular depth estimation. It is based on a generative model known as Stable Diffusion V2, which is a pre-trained text-to-image latent diffusion model, and we fine-tune it specifically for this task on synthetic data only. They use synthetic data only because real-world data can have missing values, and that will cause issues for the model's training. And also, synthetic data is the cleanest form of depth data. By adapting this powerful diffusion model, we aim to leverage its extensive visual knowledge to improve depth estimation. One of the key strengths of Marigold is its ability to perform zero-shot transfer to unseen real-world datasets. This paper makes significant contributions to the field. Firstly, it presents a simple and resource-efficient fine-tuning protocol that converts a pre-trained latent diffusion model text-to-image generator into an image conditional depth estimator. Secondly, it introduces Marigold, a state-of-the-art versatile molecular depth estimation module that offers excellent performance across a wide range of natural images. Before we go further, we must understand diffusion models. In a simple way, during training, diffusion models work by adding noise to original training images and later learn how to reverse this noise process. And during inference time, the trained diffusion model will start with a noise only and find a high-quality image. The noise is applied to the images following a Markov chain. A Markov chain is a chain of events where the current time step only depends on the previous time step. This assumption of Markov chains makes it traceable for the noise adding to be reversed later. We understand that during training, diffusion models add noise to a training image. The noise that is added is called the Gaussian noise, which is a noise that has the probability distribution of a Gaussian or normal distribution. The number of steps for adding the noise is a design choice. And then, during the denoising process, which is still during training time, the parameters of the denoiser epsilon theta will be learned by minimizing an objective function. And finally, during inference time, we start with a noise which is not always the same by the way. The noise is chosen randomly from the Gaussian distribution. And then, the learned denoiser will transform the noise into a high-quality image. Because the noise is not always the same, the image will also not be the same always. So at the end, a diffusion model is a Markov chain where in each time step, we add a little bit of noise to our image until the image only consists of noise. And later, the model learns how to reverse this noise adding process. You can find more detailed information on diffusion models at Assembly AI. Now, we can come back to understand Marigold. Like mentioned before, Marigold is based on an existing model, the Stable Diffusion V2 model, which is a text-to-image generator that has already been trained on a very large dataset. So that model contains a lot of visual information. and the work done for Marigold is to fine-tune Stable Diffusion V2 to become an image-to-depth generator. It is fine-tuned on Hypersim, which is a synthetic indoor sim dataset, and Virtual Cookie, which is a synthetic street sim dataset. Marigold functions a little bit differently from traditional diffusion models. For computational efficiency, Marigold is using a modification of the architecture of Stable Diffusion V2, where the diffusion and denoising process happen in a latent space. The latent space is like compressing the original data to obtain a new data that has lower dimension. Having a compressed data makes computations faster. Now, let's look at the forward process during training. The original model only has three channels to take in a single RGB training image, which is X. But in the modified version, they added three additional channels for the training depth image, which is D. A depth image is normally only one channel, so they simply duplicate the same single channel to become three identical channels for the depth image. And then, both of those images are encoded into the latent space by a variational autoencoder. And the noise is added to the compressed depth image only at each time step. Only the compressed depth image will have noise added. And here you can see the formula for adding the noise epsilon to the depth image at each time step or level t from 1 to capital T. The noise is Gaussian and it has a mean of 0 and the variance is the identity matrix. During the denoising process, parameters theta of the denoising model epsilon theta will be learned in a conditional way, conditioned by the compressed RGB image at each step t. And finally, we will get a denoised compressed depth image that is the half of D, and the compressed RGB image that has not changed. The compressed RGB image is only there for the conditional denoising. And again, finally, the denoised and compressed depth image will be decoded to get the high dimensional or normal dimension depth image. Because the output is three channels, it will be averaged to become a single channel. We were talking about learning the parameter theta, and this is the objective function to be minimized. It considers the square error of the predicted noise as well as the noise distribution. Now we bring everything together. They start with a training image and its corresponding training depth image. Both are synthetic. The channels of the depth image are duplicated from 1 to 3, and the input of the model is double to take in two images of three channels each. Then they both go through the encoder to pass into the latent space, and the noise is only added to the compressed depth image, which is later concatenated with the compressed RGB image. And they go through the latent diffusion unit. The first layer of the unit was modified to accept the concatenated data. The approximated noise is compared to the original noise through the objective function, and the parameters of the denoiser are learned. Remember that the noise goes from initial state without noise, then from 1 to capital T, which was 1000, right? During inference, the noise is computed from way less steps, 50 steps, and will conditionally be denoised in the presence of an RGB image to get the depth image corresponding to that RGB image. And here is the recap for the inference time. They start with a single RGB image that is compressed into the latent space, and a Gaussian noise is added and concatenated with the compressed RGB image whose depth we want to estimate. The concatenated data is passed to the latent diffusion unit for denoising for a given number of steps or levels. And the depth image predicted in the latent space is decoded and averaged to get the estimated depth image. We must note that because the noise is randomly started from a distribution, the generated depth image is not always the same. So, for inference, they have a parameter n called ensemble size to generate n depth images, a prediction for the same input. And then they use the function to combine them into a single depth image. Also, one important thing is that they normalize the values of the RGB and depth images to fall between -1 and 1. There are two reasons for that. The first reason is because that is what the original variational autoencoder expects. And for the second reason, it will make the depth images affine invariant, meaning any scene must be bounded by near and far planes with extreme depth values. By doing this, Marigold can consistently focus on understanding the relative position and sizes of objects in the image, regardless of how near or far they actually are. For the experiments using PyTorch, they start with the original Stable Diffusion v2 and disable text conditioning and implement image conditioning. For the training, they use the 1000 steps for a training time of 2.5 days. For inference, they use the 50 steps, and for each image input, generate 10 depth estimations and use a function to match them together. Here, you can see Marigold that is trained on synthetic data only, being compared to 6 other best of the best models that were all trained on real depth image data, with the addition of synthetic data for 3 of them. Also, for Marigold, during inference, they use 2 strategies. For one strategy, they make a single prediction for every image input. And for the second strategy, they make 10 predictions for every single input and use a function to merge them to become one prediction. Here, you even note one of the models using a dataset of over 12 million samples. But does the size matter? Let's look at the results. With absolute mean relative error and delta 1 score as performance metrics. As you can see in bold black color at the bottom, Marigold outperforms all the other models when it comes to using an ensemble size of 10. Even the Marigold model that is not using an ensemble size is still outperforming many of the other models by taking the second place, and underline the number means second place. And we can confirm that with the average ranks on the right. So does the size matter? Remember that Marigold is only fine-tuning another model that was trained on a very large dataset with over 5 billion image text samples. In here, with the 3D visualization of reconstructed surfaces based on predicted depth images, we can now tell that the depth images from Marigold are better in a visual way. We can, for example, see that the reconstructed depth image with Marigold not only looks visually better than the one from the real world and measured depth image, but the image from Marigold is the only one to show something that looks close to a plane. Here is another reconstruction with all 6 models and Marigold. We can also clearly see how we have better details with Marigold. But it even looks better than what comes from the ground truth depth data. In conclusions on the paper, when you read it, the results look impressive. Everything looks nice, but when you understand the paper, you see that this is a model that was chosen after trying many methods for several weeks or maybe many months. So it really looks like a brute force technique. The process presented is highly tuned for best performance on the specific dataset they chose. And if you look closely, most of the training data was indoor synthetic data. And during testing, the highest performances were also obtained on real-world indoor datasets. But the paper is a very good attempt at repurposing diffusion models. Now, we will show our replication of the fine-tuning process on a different dataset. As mentioned, the results in this paper are highly tuned, so it will be nearly impossible for us to beat the result with 2 or 3 attempts, considering the training and testing time. Thus, what we did is to try to see if we can get as close as possible to the same results they got with Marigold.
As my teammate has said, Marigold's training process as well as the ablation study are pretty extensive. This makes it perform extremely well and have extremely good accuracy on unseen datasets. That means that its zero-shot capabilities are more than solid. However, if you would want to go even beyond this performance, then we could try and not rely on its zero-shot capabilities. And instead, we could train on a specific dataset for a specific task. So our objective is that we would like to see if its training process is so good that there is no point in adjusting the checkpoint to work on a specific domain, or if there is still a little bit of performance that we can gain from additional training. So all of our experiments that we do are on top of the Marigold checkpoint and not starting from the stable diffusion. So the first experiment that we did was using the NYU V2 DEPS dataset, which is a dataset originally comprised of video sequences from a variety of indoor scenes by Microsoft Kinect cameras. So in this first experiment, we trained with Hugging Face's SFTT trainer and our custom scripts. We have trained for 3 days, and we set the learning rate to be three times less than the original one. If we look at the performance, we can see that the results are identical. And so the explanation for that is that the scripts that we used selected the best model based on the loss. And so it seems that while we fine-tuned the Marigold checkpoint, there was no better new checkpoint that would produce lower loss than the original checkpoint. So this again confirms the impressive zero-shot powers of the author's implementation. So in the experiment number 2, we've used a diode dataset, which is a dense indoor and outdoor depth dataset, and we've used all of the 25,000 images for that. And that's why we trained only for one epoch. And so the learning rate is also 3 times less than the Marigold's fine-tuning learning rate. We've done the fine-tuning by using the original code. Right, so we have 2 different configurations. If we look at the results, we can see that our fine-tuning has made the delta 1 score bigger, which is better. However, it also made the absolute relative error bigger, which is not good. So this experiment again showcases the zero-shot capabilities of the model. So let's talk about project outcomes. We successfully utilized Hugging Face's SFTT trainer to fine-tune Marigold, a diffusion-based monocular depth estimation model in the first experiment, while also managing to do it with the original scripts in the second experiment. We have also confirmed the original assumptions regarding the generalization ability of the model. And third, we now have enhanced understanding of diffusion models and have gained deeper insights into the application and behavior of said models. In conclusion, the Marigold model presents a significant advancement in monocular depth estimation, leveraging the power of diffusion-based image generation to achieve high accuracy and strong generalization across diverse datasets. Our exploration confirms that Marigold's robust zero-shot performance is a testament to the effectiveness of its training process, making it highly reliable even without additional fine-tuning on specific datasets. This is particularly evident in our experiments, where additional training did not substantially improve performance, underscoring the model's exceptional initial capabilities. However, Marigold's inference speed remains a challenge, particularly for time-sensitive applications such as autonomous driving. The model's computational demands during inference highlight an area for further optimization, perhaps through architectural adjustments or more efficient hardware utilization. In summary, Marigold stands out as a formidable tool in the field of monocular depth estimation, combining state-of-the-art accuracy with the versatility to handle unfamiliar scenes with no additional training. Future work should focus on enhancing its real-time applicability without compromising its impressive performance metrics. The insights gained from the study contribute to a deeper understanding of diffusion-based models, paving the way for us to make further advances in the depth estimation as well as other computer vision fields. That's it. Thank you for your attention.